Hello friends, in our last lecture we started talking about optical receivers, and in an optical receiver we said the front end is going to be a photodiode which takes the optical radiation, the incoming optical radiation, and produces a corresponding photocurrent, and that photocurrent would need to be converted to a voltage, and that is done using a transimpedance amplifier. And with further amplification, it is typically fed into a analog to digital converter, and then that is interfaced with a data acquisition circuit, right? So this is typically the optical receiver that we see that needs to be designed for any sensor application. We looked at the example of a PIN photodiode. We looked at why we need a PIN photodiode, why we need that PIN structure, and then we started looking at some of the characteristics of the PIN photodiode in terms of its responsivity as well as the response time, which can also be quantified in terms of the bandwidth of the overall receiver. So we stopped at the point where we defined the responsivity R as eta q over h nu, right? That's in terms of amp per watt. And since q, h and nu can be written as c over lambda, since q, h and c are all constants, we actually simplified this and said this is eta times lambda over a constant value 1.24 when wherein lambda is expressed in terms of micrometers. Okay, so let us see what this means. If we have let's say a microwatt of light incident on this, right, then what is the corresponding photocurrents that generated? Well, we can look at the responsivity of the photodiode for that. Let's say if lambda is 1.55 microns, okay, 1.55 micron happens to be a very popular telecommunication wavelength. So let's say for ease of availability of components, let's choose lambda equal to 1.55 micron. Which material would you use to pick up radiation at 1.55 micron? That would be indium gallium arsenide detector. Let's say we have one of those detectors, and for indium gallium arsenide, if you design your structure right, meaning you are having enough width so that you can pick up most of the light, you can absorb most of the light that's incident on the photodiode, you can achieve typically values in the order of 0.09. If we plug in these values, then we find that R is now 0.9 multiplied by 1.55 divided by 1.24, and if you quickly do the math, that would correspond to about 1.1 amp per watt, right? So that's the kind of number that you get for the responsivity. So what that means is if I have 1 microwatt of power that's falling on the photodiode, that's actually incident on the photodiode, then the photodiode would say generate about 1.1 microamp of current. So I'll just say approximately 1 microamp of current. Okay, and this needs to be converted to a voltage and then maybe amplified in terms of its amplitude, and then finally you're amplifying this signal so that it fills the ADC. So if you take a 10-bit ADC, you have 1024 levels in that, and if the ADC has a swing of 0 to 1 volt, let's say, if you want to use all the bits of the ADC, okay, you need to fill the ADC, which means that you need to boost up the signal, which is say 1 microamp, right? That's the maximum that's falling on the photodiode. I mean, it's a maximum photocurrent that's generated. You need to convert that to 1 volt. So what is the transimpedance gain you need? Well, you can calculate the transimpedance gain here. Gain is going to be 1 volt divided by 1 microamp. So that will be 1 mega ohm, right? So 1 mega ohm is the transimpedance gain that you need. So yes, you say, okay, 1 mega ohm, what's the problem with that? Well, we will see what might be a problem with this a little later on, but just give you a hint, these amplifiers are typically op-amp based amplifiers, and these amplifiers would have a certain bandwidth gain product, or a gain bandwidth product. Okay, so what that means is, if for example you take an op-amp 741, it has a gain bandwidth product in the order of 1 meg. What that means is you can get 1 meg transimpedance gain using this op-amp, but that will come for only 1 hertz of bandwidth. On the other hand, if you want to have at least 1 kilohertz of bandwidth, then you are limited to a gain of only 1 kilo ohm. Okay, so issues like that can actually put a limitation on this, and these are issues that we will come back and look at a little more detail slightly later. But the other aspect is, any noise that you have in your photodiode, that you generate from your photodiode, maybe because of incoming light itself is noisy, or maybe there are some processes within the photodiode that generate that noise. Any noise that you generate there is actually going to be, let's call it N of T, right? So this tends to be like an additive noise on the signal that you are trying to capture here. That noise is going to be also amplified by this 1 meg ohm, right? So this is actually an important aspect to note. The signal to noise ratio in your receiver is going to be highest at the front end. It cannot improve, as you go further down the receiver. Okay, there is a misconception that, oh, I can put amplifiers and I can improve the signal to noise ratio. No, that's not what's happening. Whenever you put an amplifier, you are boosting up the signal, but you are also boosting up the noise by the same level. Okay, so the signal to noise ratio can only degrade as it goes through all these amplifiers, because the amplifiers also add extra noise. Okay, so it will further degrade the signal to noise ratio that you have. So it's very, very important that you need to have as high signal to noise ratio as possible right at the front end itself. And the related question is, can the responsivity be increased somehow? Okay, is that possible at all? Okay, well, it turns out that is possible, and that is actually through what we call as an avalanche photodiode. So let's actually look at what avalanche photodiodes mean. Okay, so we did look at this concept a little earlier, that as you increase your electric field, okay, as you increase your electric field inside your semiconductor photodiode, you have especially at the junctions, you have you are under the influence of drift mechanism, and under that influence your velocity of the carriers can be increased. Okay, so suppose you are going to very high field levels, let's say field levels in the order of 10 power 5 volt per centimeter. Okay, if you have that sort of field levels, that's very close to the breakdown strength of the material itself. Under those intense fields, the carriers are are subjected to so much high momentum, right? They carry so much momentum that they could impede. They could actually collide with atoms in the overall matrix, right? And you could essentially, when it collides with atoms with such high momentum, it ends up generating, it basically knocks off electrons from the valence orbital. Okay, so in this case, you can look at it as electrons going from the valence band to the conduction band. Once it gets knocked off from the atom, it goes into the conduction band. So whenever that happens, of course, it also leaves behind a hole. Okay, so you generate a secondary electron hole pair due to this primary electron that's traveling with very high velocity. Okay, so this process is what we call as impact ionization. Okay, and impact ionization essentially means that you can start with one electron and that actually generates an electron hole pair, right? And then it still has, because the momentum has transferred to this new electron, now that electron can still have enough momentum that generates secondary electron hole pairs, and so on, right? And similarly, if the hole also is moving with fairly high velocity, the hole can go and generate secondary electron hole pairs as well. So that could also participate in this impact ionization. Okay, so through the process of impact ionization, you are essentially multiplying the electron hole pairs generated by, where is it all triggered? It's generated by absorption of a photon. Okay, so you start with absorption of a photon that generates an electron hole pair, but under intense electric fields that can generate secondary and further electron hole pairs. So there could be a multiplication happening, and that multiplication process can lead to an avalanche, and that's why such photodiodes are called avalanche photodiodes. Okay, so let us actually look into this a little more detail. Let's say the impact ionization can be expressed in terms of alpha. So I can draw a graph where alpha, which is typically expressed in terms of inverse centimeters, can be plotted as a function of the magnitude of the electric field. And I would say let's look at this magnitude in terms of 10 power 5 volt per centimeter. Okay, so we have 1, 2, 3, 4 and so on, and on the y-axis this could be 1, 10 power 3, 10 power 6 even. That's a huge number. So you can get multiplicative gains in the order of 10 power 6 even with this impact ionization process. Okay. So how does this look, say for silicon or for indium gallium arsenide? Let's say start with indium gallium arsenide would have something like this. You can get 10 power 3 gain, that's 10 power 3 per inverse centimeter gain, and this is for let's say electrons, right, the impact ionization coefficient for electrons, whereas for holes, right, the impact ionization is slightly lesser, the coefficient is slightly lesser. Okay, so that is typical numbers for indium gallium arsenide. So this is indium gallium arsenide. On the other hand, if you look at silicon actually has even lower impact ionization coefficient. Okay, so that is something like this. But significantly, when we look at the impact ionization coefficient for holes in silicon, so this is for electron and this is for holes, that's even lower, much lower compared to the impact ionization for electrons. Okay, so what is the corollary of this? So what does this all mean? To understand that, we need to actually, or how do you first of all trigger this impact ionization mechanism? Okay, what are the typical type of structures that are used for this? Well, you would still use a PIN structure. So I start with what we drew before, right? I would still have a relatively small P region, so let's say it's heavily doped P plus, and then you have this I region, and then you go to this region, and here you have, like before, we have a N region. Let's just call that it's highly doped N region, so we call it as N plus. Now what if we can add one more layer over here and a P with a p-type layer? Okay, so what happens in this sort of case? Well, of course we know that because of the charge transfer that happens at these interfaces, let me just represent this in a different color. I'm going to, from the p-type, I'm going to leave behind some negative charges over here. Okay, similarly on this side also I'm going to leave some negative charges. Okay, and over here I'm going to leave some positive charges. Okay, so it's fixed ions over there. So because of this, when you look at the electric field across the structure, okay, so let me just draw this out here. If I'm plotting the electric field across this structure, the electric field is going to be something like this. It's going to increase over here. This is the magnitude of the electric field, and then it's going to remain almost constant over here, and over here there is actually a sudden change in the charge density. So accordingly there's going to be an increase in the electric field, and then there's going to be a decrease. Okay, and then it goes back to 0 beyond this. So this is different. This is different in this structure compared to the previous structure of the PIN photodiode, where the electric field was constant across this entire region, entire I region. But what we have done is we have actually added one more layer over here, okay, where you have a much higher electric field. So when you apply an external bias to this. So when I connect this to just a reverse bias like we did before, right? If I connect it to a reverse bias and I increase this bias voltage, if I increase the reverse bias, then this peak is going to keep on increasing. Okay, and you can get to a point where the field levels are somewhere like this. Okay, and so that may happen somewhere over here, right? So you may achieve that threshold at this sort of a level, and any higher voltage than that that corresponds to a higher field, you're going to have even higher impact ionization coefficient. Okay, so this is what happens. So this threshold actually if you go beyond that, you start having a lot of impact ionization events happening, and then because of that you will have a large multiplicative gain happening. So essentially, like before, what we are doing is we have this incoming light Pn, and that's getting absorbed all along the eye region, and because of that you generate an electron hole pair. The electron moves this way, the hole moves this way. Okay, then the electron is actually, as it's going through this medium, it's getting accelerated, and it has so much momentum that it generates this it basically undergoes this or triggers this impact ionization, and then beyond that it generates many more electron hole pairs, okay, which are once again, because of the large field here, they are swept across this region, and then it generates photocurrent in the external external circuit. Okay, so if we were to quantify this, you would want to quantify this in terms of the current that's generated, in terms of the photocurrent that's generated, and that can actually be written as like this, dIE over dx. Let's say this is x, that's the spatial parameter. dIE over dx is given by alpha E, which corresponds to the impact ionization coefficient for electrons, times IE, okay, because the current due to impact ionization of electrons, that's what we are denoting as IE. It goes as this rate. Plus, you could also have electrons generated because of impact ionization of holes. So you could also have alpha H IH. Okay, so that is also possible. Now you'd want to say that if I can get both electrons as well as holes generating my impact ionization, okay, then I can get larger gain. So basically in this picture what it says is that if this is the threshold for electrons, my hole threshold is somewhere over here, okay, because the holes take a larger electric field to generate that sort of multiplicative gain. So that gets triggered over there. So you would say just keep increasing it, and then have holes also participate. Like this hole can now cause impact ionization, and they can also generate secondary electron hole pairs. Well, that would be a good thought, except for the fact that this impact ionization process is a random process. Okay, you cannot say that one electron is going to generate 10 electron hole pairs exactly. It could be 8 at some time, it could be 12 at some time, it could be 15 at some time, or it could be even 5 at some other time, and so on. So it's actually a random process. So we know that any random process can be characterized by a certain variance, and that variance is essentially noise in our process. Okay, so just the impact ionization process itself is expected to have a certain variance and expected to have a certain generate a certain noise. Okay, so you cannot actually have both electrons as well as holes participating, because if the holes also are generating their own random process, then the corresponding generated current is going to be that much more noisy. Okay, so there comes a point beyond which the avalanche process actually defeats the purpose. You up to a certain point you have this multiplicative gain improving the responsivity, but then beyond a certain point it also introduces so much noise that the signal to noise ratio is not increasing. Okay, so that is actually a key point to note. So you have what is called an optimum bias voltage as far as operating avalanche photodiodes are concerned. The optimum bias voltage is determined by how far is the threshold for the holes from the threshold for the electron. Okay, so from that perspective you can say that in silicon the difference between electrons and holes are so much higher, the impact ionization coefficient, that the threshold for holes is at a much higher level. So you're able to keep increasing your bias voltage and keep getting higher and higher multiplicative gain for a silicon photodiode without incurring extra noise, up to a certain voltage. So that voltage is much higher for silicon compared to indium gallium arsenide. So you're able to effectively get much higher optimum gain values for silicon compared to indium gallium arsenide. That's the takeaway point. Okay, but in general, this is what we call as this structure is what we call as a separate absorption, because this is where the absorption is happening primarily, and this region is where the multiplication is happening. So it's a separate absorption multiplication photodiode. So that structure is called a SAM-APD. Okay, so this particular design is called a SAM-APD, and that's one of the more popular APDs that you find out there. Of course, like I said, this is not only generating a current due to these electrons, it's also generating a current due to holes, right? And that's actually going in the opposite direction. That's why there is this minus sign here, but that's also given by alpha E IE plus alpha H IH. Okay. Now we can solve these rate equations, and with certain boundary conditions. Boundary conditions are essentially saying that the avalanche process is triggered by this electron coming from this region, and there are no holes coming from this region. The hole current is 0 when you start from with some of those sort of boundary conditions, and the charge neutrality, which says that whenever an electron is generated, there's also a hole that's generated, right? So the electron current and the hole current is the sum of both of those is a constant, and that's uniform across the entire structure. So you can do all of this, and then you can actually represent, you can actually get an expression for this. You can solve these equations and you can get an expression for the multiplicative gain. Okay, that gain value happens to be, you can call that as M. Okay, M is actually expressed in terms of the impact ionization coefficients, and it's convenient to represent this ratio of this impact ionization coefficients. Let's say this is the, this is the II ratio, impact ionization ratio, Ka, which is given by impact ionization coefficient for holes divided by impact ionization coefficient for electrons. Okay. So just a quick word about the value of Ka. The value of Ka can be anything from 0 to infinity, right? So it depends on the relative values of the impact ionization for holes and electrons. So which is a good value to get optimum gain? Well, you can say that if Ka equals to 1, in which case impact ionization coefficient for holes is the same as that for electrons. If that is the case, then both of them have the same threshold and both of them are participating in this process, in this avalanche process, and they generate a lot of noise. So overall, you were not going to get a very good gain from this process without incurring significant noise. Okay, so it becomes counterproductive. On the other hand, if Ka is closer to 0, let's say alpha E is far greater than alpha H. Let's say for example in silicon, that's what we see. Alpha E is far greater than, its order of magnitude greater than that for holes. If that is the case, then Ka is a very small value. Okay, and that means there is a large gap between these two thresholds. So only one type of charge carrier, in this case the electron, is generating all the impact ionization events. Okay, so that is actually a preferable condition, and then that would also result in a higher multiplicative gain. So let's actually quantify that. So if, like I said, if you work out these rate equations with the boundary conditions and all, you come up with an expression like this, which is given by m equal to 1 minus Ka divided by exponential of minus 1 minus Ka multiplied by alpha E Wm. So I have not defined Wm yet. Wm corresponds to the width of this multiplication region. So this is my Wm. Okay. So this minus Ka. Okay. So that is actually the expression for the multiplicative gain, which depends on Ka, which is actually a constant for any given material. So you can pick the material based on its value of Ka. And then what are the other parameters? You have alpha E, okay, which you can control. How do you control alpha E? Well, if you go back and look at this graph, it's controlled by controlling the electric field. And how do you control the electric field? By controlling the bias voltage that you have here, the V bias, right? So by controlling V bias, you can actually control alpha E, and Wm is actually a parameter that you design up front, it's a relatively small value, smaller than the width of the intrinsic region typically. Okay, so so that is actually the expression for M. So let's actually look into this in a little more detail, and to do that, let me actually try to copy this. Okay, and let me just go to a fresh page. So what we are looking at is this expression for the gain. This is actually the multiplicative gain for an APD, right? So let's just plot this and see what it means. Okay, so on the y-axis, I'm looking at M, which starts from 1 and it can go to 10, 100 and so on. Whereas in the y-axis, I have alpha E WM, which is actually representative of the V bias, because that's what you're changing to change alpha E WM. Okay, and so that is 1, 2, 3, 4 and so on, right? So if you have something like this, let's actually look at two extreme conditions. One is where Ka equals to 0. Okay, if Ka equals to 0, then this becomes 0, this becomes 0, then this also becomes 0. So then you have exponential of alpha E WM. Okay, so that would correspond to something like this. So this is actually Ka equal to 0. Okay. And then the other condition is when Ka equals to 1. Okay, if Ka equals to 1, then this becomes 1, and then if you substitute here, this is also 1, so that's 0. So the whole thing is 1. So 1 minus 1, that is, the denominator is going to be 0. So that's indeterminable. So you use L'Hospital's rule, and then you work it out. What you will find is for that condition, it will tend to be asymptotic. It will work out to be 1 over 1 minus alpha E WM, right? And so that will be asymptotic with respect to this value of 1. So it will be something like this. So this is for Ka equal to 1. And for other values of Ka, for example, silicon is Ka is 0.1. So then it will look something like this, 0.1 for silicon, and Ka is 0.5 for indium gallium arsenide. So this is Ka equal to 0.5 indium gallium arsenide. Okay, so you look at this picture and you say Ka equal to 1 seems to be a very good condition because of the fact that even for very small values of alpha E or very small values of bias voltage, you can get a very high gain. But that is only one part of the picture. We have not actually started talking about noise that's generated from an avalanche photodiode. From a perspective of noise, you will find that this is actually the most noisy condition. Whereas K equal to 0, it although it says that it's a very slowly evolving exponential, nevertheless you'd find that for this condition you will have you'll be able to go to much higher levels of gain. Okay, so we will look at some of these finer features soon in the next lecture.